Hello everyone, my name is Juan Cruz. I'm a Ph.D. student of the Universidad Nacional de la Patagonia San Juan Bosco, and today I'm going to talk about my doctoral thesis called Effect of a Biopolymer on the Mechanical and Microstructural Behavior of Oil Well Cement for CO2 Geological Storage. The project Discontinuities in CO2 Storage Reservoirs allowed me to spend some time at the Universidad Politécnica de Madrid and the École de Ponts ParisTech, where I was able to make some progress in my experimental tests and numerical simulations. Now let us look at one of the problems that may arise in the context of CO2 geological storage.
How can long-term carbonation affect cement? Let us consider a wellbore with the casing and the cement sheet already protected it from the surroundings. In some reservoirs, we can find CO2 in a supercritical state after injection. So what happens to CO2 at this point? It acquires the density of a fluid but with a viscosity of a gas, and also a higher CO2 concentration. That increases the carbonation process, as can be seen in this sample. Carbonation leaches portlandite, which lowers the pH level of the medium and can lead to corrosion of the casing. It also precipitates calcium carbonate. The chemical reaction of CSH also produces carbonates and amorphous silica, which can decrease mechanical performance and loosen structural integrity. If conditions permit, the dissolution of calcium carbonate can reduce the cement mass, thus progressively disintegrating it. That is why we need to find a way to improve the resistance of cement to supercritical carbonation. The use of new additives can serve this purpose. Now, let's see what bacterial nanocellulose is. Nanocellulose is the smallest fiber size that can be found in a cellulose fiber. It has width of 20 to 40 nanometers and length of up to 1 micrometer, so it has a large specific surface area. At the microscale, it is similar to a gel, but under the microscope, the cross-linked nanofibers can be observed. Some advantages in the use of bacterial nanocellulose are that it is an environmentally friendly material, it has high mechanical properties, and it is a thermally resistant material. It can be added in small quantities, 0.05 to 0.20% by weight of cement, and it has a background in reducing cement microcracks.
Based on these concepts, we propose to determine the effects of bacterial nanocellulose on cement. For this purpose, the work was divided into three parts. The first one consisted of characterizing the effects produced to cement by the addition of bacterial nanocellulose. The second one consisted of analyzing the behavior of both cement types subjected to supercritical carbonation. And the third part involved simulating the carbonation process of experimental samples. The experimental program consisted of analyzing the mechanical and microstructural behavior of the samples with bacterial nanocellulose. The box on the left shows the experimental test performed on non-carbonated samples. For instance, tests of flowability, thermal resistance, and mechanical strength, as well as the determination of the hydration degree of cement. The box on the right shows the test performed on carbonated samples. In this case, microscopy and ultrasonic wave measurements were added. I'm not going to detail each test, but I will show you some results obtained from them.
Can we use bacterial nanocellulose to improve cement properties? Let's see what happens in uncarbonated samples. In the free fluid test, we observe a lower percentage in samples with bacterial nanocellulose. This indicates that less sedimentation occurred, which may prevent the fluid breakout. While in the thermogravimetry test, we can observe a higher amount of cement hydrates and a higher degree of hydration. The increase in hydration is produced by water retained by the bacterial nanocellulose fibers. If so, does the water retained in the mixture increase the porosity of the cement? Well, in fact, no. On the contrary, the retention of water by the fibers allows for fewer capillary pores, reducing their porosity and modifying the characteristic peak in the pore size distribution. Also, total porosity, which is the sum of capillary porosity and gel porosity, the smallest pores, is maintained. Now let's see how cement with bacterial nanocellulose behaves under supercritical carbonation. The equipment used consists of a CO2 pump, a titanium cell, and a heater. Here is a schematic of how it works. In brief, the samples are placed in a holding grid and CO2 is pumped in. The pressure is released a little to evacuate the air contained in the upper part and heated until a pressure of 20 MPa and 90 degrees Celsius is reached. This allows the samples to be in a supercritical CO2 environment. Carbonation changes the surface color of the sample from gray to brown, and some cracks can also be observed in some of them. In a cross-section of the specimen, we can see the degradation process. Mercury intrusion porosimetry, X-ray diffraction, and total porosity tests were carried out on samples from the core and near the outer rim. The MIP results indicate that the core of the specimens with bacterial nanocellulose was less affected. X-ray diffraction results show a large amount of aragonite on the exposed surface and few carbonates at the cement core. There are no major differences in the crystalline phase of the cement with or without bacterial nanocellulose. The total porosity near the exposed surface decreases while in the interior it increases. The total internal and external porosity is lower in cement with bacterial nanocellulose. When performing compressive strength tests, results indicate that all specimens decreased their mechanical performance. Nevertheless, specimens with bacterial nanocellulose were less affected. They only lost 10 to 20% of their compressive strength and Young modulus, while net cement lost up to 35% of these parameters.
In the experimental modeling, the model simulates the advance of the carbonation front in cement subjected to supercritical CO2 and the changes generated by the chemical reactions using the classical balance equation of power continua based on conservation of mass and momentum. A homogenization technique is then introduced to calculate the poroelastic moduli of the cement paste during the dissolution and precipitation processes induced by its carbonation. All cement components have to be considered in the homogenization analysis in terms of their mechanical contribution to the overall stiffness. Anisotropic damage is considered in the numerical analysis. The damage stress is based on the decrease of the effective area due to reappearance of microcavities. For this case, we consider anisotropic damage, which allows us to express the damage as a function of a single variable d. A damage criterion is introduced through the definition of a geosurface in the stress space. This model adopts a Drucker-Prager criterion. Finally, the mean and deviatoric stresses are evaluated from the imposed deformation and the homogenized moduli. Once the stress state reaches the Drucker-Prager criterion and is greater than 0, the damage is calculated as a function of an increment of deviatoric and volumetric deformations. From this damage, the new damage stress and the mechanical moduli are calculated. First, the result of a uniaxial compression test on cylindrical specimen is simulated. The effect of isotropic damage can be seen in the left image. Assuming that it's loaded until the geostress and then unloaded, damage occurs on the specimen, which reduces its elastic properties. When it's reloaded, the stress reaches the same maximum value but with different modulus of elasticity. The model determines that the elastic moduli are directly affected by the damage produced. From the central image, we observe how the bulk modulus varies with time, following the loading and unloaded sequence plotted in the previous image. The next image indicates that the simulation continues until the moment when the damage is equal to 0.5, so the deformation rate is maintained until that point is reached. The carbonation of a cylindrical sample can then be modeled and the variation of different parameters over time can be determined. The advance of carbonation can be seen in the left image. The central images show the decrease of calcium hydroxide and CSH, while the image on the right shows the precipitation of calcium carbonates. The graph below shows the result of the experimental samples, non-carbonated and carbonated for 30 days. The numerical simulations approximate the values after 30 days of supercritical carbonations. We conclude that bacterial nanocellulose decreases the free fluid content, resulting in less sedimentation, increases the hydration of cement, and decreases capillary porosity. This increase in hydration was likely the reason that cement with bacterial nanocellulose had a uniaxial compressive strength up to 20% higher than net cement. After supercritical carbonation, specimens with bacterial nanocellulose show higher values in their mechanical properties compared to net cement in absolute and relative terms. They also show less amount of carbonates either at the core or near the surface exposed to CO2. The chemohydromechanical model proves to be a useful tool for simulating the carbonation process, which can be used to simulate different carbonation scenarios. I would like to thank my supervisors who participated in this project, Diego Manzanal and Jean-Michel Pereira, and I would also like to thank the support provided by Sebas Gavezlou. I hope you enjoyed this presentation and thank you for your attention.